Hi everyone, welcome back to Chapter 9. So today, as I said, we're going to be covering Chapter 9, and Chapter 9 is going to be based upon what we learned in the previous chapters, Chapter 6, 7, 8. Now, what we're going to be doing is we're going to be making these inferences about two different samples. All right. Sometimes the samples might be the same amount. Sometimes the samples might not be the same amount. All right. So to start off section 9.1, we're going to be working with two proportions. Now, again, when we work with chapter 9, we're only going to be working with two types of unbiased estimators. We either deal with the unbiased estimator, of x bar, in other words, the sample average that we're going to be observing, or we look at the proportion for the sample that we're looking at. These are the only two methods that we can use in order to make inferences about a certain population, because again, these are unbiased estimators. So whether we use the mean or the proportion, we're going to have to use one or the other. All right. Now in section 9.1, we're going to be working with two proportions, which means we're only going to be working with p hat in this particular case. So let's look at this particular scenario. In this scenario, it says, think about whether you plan to vote for the next presidential election this year in 2020. And let's say I split the responses into two groups, females and males. So there are going to be two proportions here. Now, in the first proportion, I'm going to ask the females. If I ask the females, how many of you plan to vote for the presidential election, there's going to be a certain amount of females that answered yes, and some of them that answer no. Okay, now if that's the case, then what I'm going to do from my observing standpoint, I'm just going to say, hey, that's going to be a certain proportion of females that said yes, they do plan to vote in the next presidential election. Let's say that it was about 54% of the females said yes, they are going to vote in the next presidential election. Now say I hold the same question for the males. All right, how many males are going to vote in the next presidential election? Well, I'm going to get a response here. That response could be, again, some percentage that I look at, or some proportion that I look at within the responses of the males that are going to vote. So in that sense, I could get something like, let's say, 0.51. All right, and again, this is just saying that 51% of the males are going to vote in the next presidential election. The first one, the probability or proportion 1, says that 54% of the females are going to vote in the next presidential election. All right, so the question then becomes: is there a statistically significant difference? Well, at this point in time, we can't exactly answer that yet because we don't know it. All right, but this is one of those underlying questions that we want to pose, because at the end of the day, this is what we're going to be looking for. All right, so is there statistical difference? We don't know yet. We don't know. Sad face. But we don't know it yet. All right, which means we are going to get there. And when we get there, it's going to be really nice, because again, we're going to be able to say, hey, there is a statistical significance, at least difference-wise, between these two proportions that we're observing. Now, what we really care about is not that the proportions are the same. Right? So we don't actually care about the proportions here. We only care about one thing, and that one thing that we really care about is whether they are the same or not. All right, so that's going to be a big case that we're going to be looking at. Right? So in 9.1, we're only going to deal with independent samples. That means these independent samples are going to have to be for qualitative variables. In other words, we're going to be looking at categorical data. All right, so this is a type of data that we now start observing. How many how many answered yes, how many answered no, right? So we're taking this response that is a qualitative response, and we're going to slowly convert this into a quantifiable item. That way we can run some inferences about these samples in order to achieve what we want about the population. All right. Now, the logic behind this, all right, well, what we're going to do is we're going to start assuming that the two proportions are what we established here, the same. All right, if we find enough data, then we're going to be able to refute that, and we're then going to be able to say, hey, this does not hold anymore, therefore they must be different. All right, so the logic starts where we're assuming that they are the same. So the two proportions here for the populations are going to be the same. So if they're the same, what happens when we subtract the same number from itself? Well, we get 0. So what we're going to have to do first is we're going to have to collect these sample proportions. So we're going to have to collect these sample proportions, and we're going to have to find the proportions for each of those samples. In other words, we want p hat 1 and we want p hat 2. Again, these are just sample proportions. So when I look at these sample proportions, by definition, this should be that p hat 1 is equal to the favorable outcomes in the first sample divided by how many were in that initial sample. P hat 2 is a proportion that had that favorable outcome out of all of the samples that we took. So we're then going to see how close is the difference within these two proportions, and is that difference anywhere close to 0? Because again, if that difference is close to 0, then great, that's going to support our hypothesis or this assumption that we made from the very beginning. If it's not anywhere close to 0, well, then we have some issue, and then there is going to be a statistical significance that we then start looking at because of their difference. So the logic here, again, when we want to do this testing of the null and the alternative hypothesis, is that we want to start off with the null hypothesis saying that the two proportions are equal to one another. In other words, if they're equal to one another, then their difference must be 0. The alternative is that we're trying to collect data to see if we can refute that hypothesis. So what we then have to do then is we then have to start analyzing, what if the two sample sizes are equal to one another? Or sorry, not sample sizes. What if the two sample proportions are equal to one another? In other words, p hat 1 is equal to p hat 2. Well, at this point in time, if that's the case, then there is no statistical significance because these two values are close to 0 themselves, which means we fail to reject the null hypotheses. And again, we're failing to reject the null hypotheses because if the sample proportions are equal to one another, then it must mean that there is no difference in the population proportions. So again, we fail to reject the null hypothesis. All right, so number 2 here, if p hat 1 is greater than p hat 2. All right, so again, we're looking at this in the particular sense that one is going to be greater than the other. All right, well, in this particular case, if p hat 1 is greater than p hat 2, again, we are still going to fail to reject. All right. And again, this is a case because look at our alternative hypotheses. The alternative hypothesis says that we want proportion 1 to be less than proportion 2. But if within the sample we get the opposite of that, that means we cannot support this alternative hypothesis, which means we cannot reject the null hypothesis. In other words, that stands for fail to reject for that null hypothesis. Now, what if we actually get the outcome that we want, but it only happens by a little bit, meaning that p hat 1 is less than p hat 2 only by a little amount? In other words, is there a big statistical significance? Now, your answer to that is going to kind of lie in the realm of what does it mean to be statistically significant? We want to move 2 standard deviations away or more, right? That 5% rule that we were initially looking at from the beginning chapters. So if p hat 1 is less than p hat 2 only by a little bit, then there is still not enough information, or there is not enough data for us to be able to refute this hypothesis. In other words, we are still going to fail to reject. All right, and I'll explain what all that means with pictures down below in just a little bit. Now, what happens if we actually get that desired result where p hat 1 is going to be less than p hat 2, but now it's going to be less than that by a lot? Meaning there is a big statistical difference at that point in time. In other words, we moved away more than 2 standard deviations, which means we are going to reject the null hypothesis at this point in time. And it's only when it is varying by a lot. So varying by a lot, what does that mean, right? We want to make sure this is not ambiguous to anybody reading this. Being a difference by a lot is going to mean that we have enough data to reject that hypothesis. All right, to reject the null hypothesis. Now, when we do that, I'll show you in just a bit. I'll show you on this side over here as to what the pictures mean for that. All right, so let's keep going down below just a little bit more. So the samples that we are going to be looking at are going to be simple random samples, and they're going to be independent. Whoops. And they're going to be independent. There we are. And so we must have at least 5 successes. In other words, when we're looking at our sample size multiplied by their proportion, we should be able to get that we at least have at minimum 5 successes and 5 failures for each individual sample. All right, so again, we must be able to hold that. Now, the types of tests that we look at. The first type of test, well, since the alternative hypothesis is not equal to, this is actually going to provide us a two-tailed test. So two-tailed test. Now, if our alternative hypothesis is P1 less than P2, then this is going to be a left tail test. And if P1 is greater than P2, this is going to be a right tail test. And we must always identify first what type of test we have. All right, so once we're able to identify this is my null hypothesis, this is my alternative hypothesis, the third thing is to identify what type of tail test are we observing. That way, when we start looking at our level of significance, we know whether we're going to divide by 2 or whether we're not going to divide by 2. That, in the sense, is what step number 2 is in this particular case, right? It's going to say if the level of significance is not given, and the level of significance that we use is always alpha. So if it is not given, then we use alpha as 0.05. Now, why do we use alpha as 0.05? Well, if you remember, when we were looking at making the statistical significance, or something that is significantly high or significantly low, we always use that 5% rule. And remember, that 5% rule stands for those 2 standard deviations that we like to observe, which naturally means if we're not given a level of significance, then we automatically assume that level of significance to be that level of 0.05. All right. Now, this, again, is going to depend on the seriousness of making a type 1 error. All right, so depending on how serious that type 1 error is, we might actually change this level of significance. All right, now, the formulas. We're going to be using 2 types of formulas in this specific section. Those 2 types of formulas are given here. We're going to be looking for a test statistic. That test statistic is going to be Z star. And Z star is going to be given by this formula. Secondly, we're going to be using a point estimate, because again, we can't make inferences without having these point estimates. Now, we must be careful when we're doing these point estimates to always make sure that we account for the 2 separate samples that we're going to be given. So now that we have that, let's go back over here and let's look at what I was initially talking about, whether we're going to be moving a lot or a little bit in order to determine that statistical significance. So we're going to be using either the critical value or the p-value method. On your exams, when you're looking at Chapter 8 and Chapter 9, I'm going to be looking for one of the 2 methods in order for you to conduct or for you to extract a conclusion. All right, I want to know, can you do this using the critical value method, and can you also do this using the p-value method? So there are specific questions on an exam where I will ask that you must do that problem using the critical value method, or you must do that problem using the p-value method. All right, so here we see the p-value method, and again, both of these methods are exactly the same. One method, the p-value method, just uses the comparison of areas, these shaded portions, whereas the critical value method just uses a comparison of the z-values. Again, they're both the exact same method, but they just use different comparisons. One talks about area, the other one talks about the z-values. All right, so we typically then want to know, hey, looking at our 2 standard deviations here, these are your test statistics. Sorry, these are your critical values that you look at. When you're looking at those critical values, you then have to see, where does your test statistic fall in respect to those critical values? So if my test statistic fell inside of that critical region, then I'm going to reject that null hypothesis. Specifically because once it falls in there, in that region, in that critical region, then we've exceeded the 2 standard deviations, which then makes this statistically significant. All right. Now, if that's going to be the case, well, looking at that description here, when we were looking at by a little and by a little just means we didn't move past that 2 standard deviations. And even though it might satisfy the requirements that P1 must be less than P2, again, there is no big difference because we didn't fall in that critical region. So that's why we have that terminology of a little or a lot that we're going to be analyzing. So the last step is just to write a conclusion to that specific claim. All right, so I know you all have been waiting for this, so let's jump right into this example. This example says that an insurance company is concerned that men are more likely to speed than women. Whoa, that actually might be the case. Interesting. So, in a sample of 500 randomly selected women, 27 have been ticketed for speeding in the last year. In a sample of 250 randomly selected men, 26 have been ticketed for speeding in the last year. Use a 0.05 significance level to test the insurance company's claim that the percentage of women ticketed for speeding is less than the percentage of men. All right, so we got some work to do here, and what we're going to do is we're going to start extracting everything that we know from here. All right, now the first thing is that we want to establish what is a null and what is alternative hypothesis. So what I'm going to do really quickly is I'm going to state here that I have some sort of null hypothesis and I have some sort of alternative hypotheses. All right, now in order for me to be to extract what it is that I'm identifying here, or what it is that I'm going to work towards to, I'm going to look at the very last sentence. The very last sentence says that I must use a 0.05 significance level. All right, that's nice, that's in the bag, to test the insurance company's claim. All right, so here goes the claim. Here's the alternative hypothesis. The percentage of women ticketed for speeding is less than the percentage of men. All right, there is my alternative hypotheses. All right, so percentage of women, I need that. So how about we label this percentage of women P1. All right, so not too bad. All right, so we're going to label that P1 is less than, so this part less than, that's going to be this inequality here, the percentage of men. So the percentage of men in this particular case, I'm going to identify this as P2. So naturally, my alternative hypothesis now becomes that P1 must be less than P2. Now, English, as a translation here, says that the percentage of women will be less than the percentage of men in this particular case. So what is then our null hypothesis? Well, the null hypothesis always stays exactly the same, that P1 must be equal to P2. Again, we're trying to refute this specific hypothesis. We're trying to find if there's anything different within this data that is going to be given to us. All right, so null and alternative, done. We're good with that. So once we've identified this, let's go ahead and let's identify what type of test is this going to be. All right, so P1 less than P2, that's going to be a left tail test. Awesome. So now that I've identified it's a left tail test and I have my null and alternative hypothesis, now I'm going to go start setting everything up. In order for me to conduct this test, I'm going to need a test statistic, and looking at all of my information, I need to know what is P hat 1, what is P hat 2, what is also P bar in this particular case, and what is Q bar in that case as well. So I have a lot of work ahead of me, and that's what we're going to do next. We're going to start extracting all of this work in order for us to be able to come to a conclusion here. So I'm going to do the work on outside of the sheet of paper, and I'm going to do this right on here on the blank space that I have on the right hand side of my screen. So here we go. Let's see, let's do this in orange because I want P1 here. So this is going to be women, and then we're going to have men. All right, and what you're going to see me do here is I'm going to draw a table so that I can keep all of this information organized. And the reason I want to keep it organized is because I'm going to be extracting a lot of information from here. So let's go to the information that was given to us. All right, so it says in a sample of 500 women. All right, so we got here 500 women. So let's see, sample of 500 randomly selected women. All right, 27 have been ticketed for speeding. Okay. So what I have here is I have a sample, and we're going to call this sample 1. Sample 1 is going to be women. N1, again, sample notation for sample 1 for women is that we had 500 women. Now, how many were ticketed? In other words, how many had that favorable outcome? The favorable outcome that we're looking at is that they were ticketed, which means 27 of them were ticketed. Now, this is all that we need for the women. Let's go on to the men. For the men, how many men were then sampled? Well, in a sample of 250 randomly selected men, 26 have been ticketed for speeding. Okay, awesome. So here we have sample 2. There we are. Sample 2, this is n sub 2, and this is going to be 250, and x sub 2, meaning the favorable outcome that we're observing, was 26 of them. All right, so now that we have this, let's go ahead and let's start extracting everything else that we need. Now, I'm actually done with this piece right here. All right, that's the information that we extracted. The information that we now need to extract indirectly is going to be p hat 1. So what is the first proportion, or what is the sample for proportion 1? Well, that's going to be 27 divided by the 500, because 27 women out of those 500 were ticketed for speeding within that last year. So what I'm going to do really quickly is I'm going to put this into my calculator, and I get an answer of 0.054. Notice I'm not rounding. If it doesn't give me a long decimal, then let's just keep that. Keep it as is. So proportion now for sample 2. That was the 26 men that were ticketed out of the 250 that were within that sample. So again, putting it into your calculator, you should be able to get, 0.104. Awesome. So now that we have all of this information ready for us, what I also need to do is I also need to find what is P bar. All right, because again, if you look at your test statistic, in order for you to get the test statistic, we need P bar and we need Q bar. So let's go through and let's figure that out now. All right, I'm going to use a different color here, and I'm going to go with this kind of a pinkish color here. All right, so here goes P bar. In order to find P bar, we need to take the addition of the two favorable outcomes. One was 27, the other one was 26. There we are. And then what we're going to do is we're going to divide by the two sample sizes. Well, the first sample size was 500, and the second sample size was half that amount, which is 250. And so what you're going to do is you're just going to enter this into your calculator, and you're going to get, let's see, if you do the addition first, you're going to get 53 divided by 750. Now, once we get this, what I'm going to do here is I'm actually going to go through and I'm actually going to round this specific value. Now, this value is very long decimal. It is 0.0706666666667. All right, it's a really, really long value, and it's going to keep on repeating forever. So what I'm going to do is I'm just going to truncate this to about 0.07. Now, if you wanted to do 0.071, that's perfectly fine. All right. Now, aside from this, I'm also going to need to find Q bar. Now, Q bar is going to be a very similar process as to how we were finding P hat and Q hat, or P and Q. In this particular case, it's just 1 minus 0.07, or it's the complement of P bar. In this particular case, we get 0.93. There we are. Looking pretty good. Now, we need that test statistic. All right, so in order to extract this test statistic, we need that formula. So I'm going to be using this formula that is going to be P hat 1 minus P hat 2 subtracted by P1 minus P2 divided by P bar Q bar divided by n sub 1 plus P bar Q bar divided by n sub 2, and that denominator is then square rooted. So let's make all of these insertions here. All right, in order to get my test statistic here, I'm going to go with p hat 1 minus p hat 2. All right, all that work is done up here, so I'm going to extract that. That was 0.54 minus 0.104. There we are. That's p hat 1 minus p hat 2 minus p1 minus p2. But remember, the assumption that we have under p1 minus p2 is that they're both equal to one another. So what happens when you subtract a number from itself? Well, you naturally get 0. And this is always going to be the case for us. We're always going to be using 0 for this last part of p1 minus p2. Now, we need p bar, q bar. All right, so let's go with p bar and q bar. So p bar in this particular case is going to be 0.07 multiplied by 0.93. And we're going to divide this by N1. And N1 is that 500, because we had 500 in the original sample, plus, again, I still need that p bar, and I still need q bar. There we are. Divided by the second sample size, which should be 250. And then we take the square root of that denominator as such. All right, very nice. Now, what I'm going to do really quickly is I'm going to go to the TI and I'm going to start inputting this into that calculator. All right, so I want you to then follow me along to that. All right, so here we are on the TI 84. So what I'm going to do really quickly is I want to enter it exactly as it was on my screen, which means I need a fraction bar. Now remember how we do the fraction bars. All right, what I'm going to go to here is I'm going to go to alpha and I'm going to hit F1 here. All right, that's that y equal to sign. And I'm going to select the very first option, which is numerator and denominator form, exactly like this. And what I'm going to do is I'm going to start inserting my numerator. The numerator, you can insert it exactly as it was. If you open the parenthesis, we're going to have 0.54 minus 0.104, just like this. Close the parenthesis. Now, I'm going to say this once, that I don't need to subtract by 0. Because if I'm subtracting by 0, it is not going to affect that numerator. Which means at this point in time, we don't need to worry about subtracting by 0. If you want to go ahead and do so, please by all means go ahead and do minus 0. But I am not. Denominator now. The denominator has a square root. So I'm going to access that square root first. So I'm going to press second, square root. There we are. Now within that square root, I need another fraction. Okay, so I'm going to go through my fraction operation. Here we are. I need the first one, so I'm going to press enter. And I'm going to start typing in what was that p bar, which was 0.07, multiplied by 0.93. And then I need the divisor here, so I need to go down to the denominator, and I'm just going to use my down arrow here. So the down arrow, and the first one was 500. Just like that. Now, if I'm done with the first fraction, I'm going to go through and I'm going to tell the calculator that I'm done with the first one, but I'm not hitting enter. Instead, I'm going to hit the right arrow. Press the right arrow and that removes you out of that first fraction. Now I want to add a second fraction, so I'm going to go through the whole process again of inserting that fraction, and I'm going to go ahead and slowly start inserting p bar once again, multiplied by q bar as such. Move on down so that we can go to the denominator, and that denominator was 250. So now I want you to then look at this particular piece here. This on screen is the exact same format that I had it written on the actual page that I'm working on. All right, so really quickly, I'm just going to go back to that. There we are, and I'm looking at this piece right here. So it looks exactly identical as to how I have it written on my TI. So all we then have to do is just press enter. We press enter and we should get a really nice answer. Now, I'm kind of freaking out because this answer is not the answer that I have here, and I think I actually see the problem here. My p value, my p hat 1 is not 0.54, it's actually 0.054. And the reason I'm freaking out is because this corresponds with a test statistic, and a test statistic or z-score of 22 is very, very large. So I'm going to go ahead and I'm going to resubmit this again. There we are. And let's go ahead and let's change this. There we are. There we go. Now I'm going to insert a 0 in there. Whoa, entered it at the wrong place. Delete that. Here we go. So I'm going to insert a 0. There we go. Press enter, and there it is. Boom, problem solved. Whew. Problem solved, crisis averted. Now, z-scores, remember what we said. Z-scores are always truncated to 2 decimal places, which means this z-score is going to be negative 2.53. Okay, so let's go back to the page and we'll go ahead and write it on there. All right, here we are. So that means that our test statistic that we found, this test statistic is going to be negative 2.53. Now, I want you to then hold on to that because let's start looking at this left tail. So left tail, that means that we're going to be moving towards our left, and negative numbers are typically to the left of the mean, and the mean here is that standard normal mean of 0, which means we're on track for this to be a left tail test. So that's kind of nice, right? That we start looking at this and we're getting everything that we need. All right, so now that we have this, we can either do this with the p-value or we can do this with the critical value method, one or the other. All right, we're going to illustrate both methods. That way we can feel comfortable with what it is that we're observing. All right, and that way during the exam you can choose whatever method you'd like. So the first one, I'm going to go with my favorite. My favorite is using the critical region method. All right, it's not comparing the p-values. The p-values, yeah, we'll get to that in a little bit. But I like more the critical region. So what I'm going to do with the critical region here is I'm going to go through and I'm going to start extracting what is my critical value. So the first thing that I want to do here is I want to find the critical value. So the critical value, in other words, I'm finding z sub alpha. And notice it's only z sub alpha. I am not dividing by 2 because this is a left tail test. If this was a two-tailed test, I would divide this alpha by 2, but since it's not, I don't need to. And that, oops, excuse me. And this in here is going to be z sub 0.05 because our alpha level was 0.05 as such. All right, so let's go through this process. Z sub 0.05. Well, in order to do this, I'm going to need this inverse norm to find the z value. So I'm going to do inverse norm, and then I need to know what is the area that I'm looking at, which in this case is 0.05. Then I'm going to tell it what kind of tail I'm working with. Is it going to be a left tail, right tail? Is it the center? All right, and then I also need to find, well, what is the mean and what is the standard deviation? So the mean here is 0, 1, and this is going to be a left tail. All right, so let's go to the TI and let's see if we can pull this off. All right, so here we are. So I'm going to go through and I'm going to start accessing my inverse norm. All right, we should be pros at this by now. So the area that I'm looking at is at 0.05. The mean is just going to be the standard normal mean. Standard deviation is just 1, and I'm working with a left tail, so I'm just going to insert left. Here we are, which is 0.05, 0, 1, and then left. And then we get a value of negative 1.64. Now again, we're doing the rounding here because this is still a z value. So let's go back to the page and write that. I have no idea what happened there. You were looking at my ceiling. All right, so here we go. So the answer that we got here was negative 1.64. Now, looking at negative 1.64, what I'm going to do is I'm going to go through this small calculation here. So this is going to be 0, negative 1, negative 2, and negative 3. And what I'm going to do is I'm going to identify what my critical value is. My critical value is negative 1.64. Negative 1.64, that's right in here. All right, so that's negative 1.64, and this is my critical value. I'm going to abbreviate this with CV. That means anything to the left of this critical value is going to be within that critical region. If my test statistic falls within that region, then I must reject. And my value here, let's do this in red, my value here of negative 2.53 falls right in here. Negative 2.53. This is my test statistic. So it falls in the region, which means I must reject the null hypothesis. Right? Now, I typically call this shaded region the friend zone. And the reason why I call it the friend zone is because if you have a friend and you're attracted to the friend and you want to court the friend, then you have a shot at it, right? You have a shot at being with your friend. However, if let's say that you have no shot whatsoever, that means you're put into the friend zone. You're going to stay the friend forever and you're not going to be able to do a relationship. So naturally, when we're in this region, that means that they're rejecting us. Right? That means they're rejecting that friend. So I call it the friend zone, right? So if you're in the friend zone, you've got to be rejected. So in this case, my test statistic falls in that friend zone, which means we must reject the null hypothesis. All right. So this is known, this part right here is the process that we use for that critical value region. Now, if we didn't use that critical value region, that means we can use a p-value method. So let's start then looking at that p-value method. And I'm going to do this here. So the p-value. So this first one was the critical region. That was down there. And now I'm going to be working with the p-value method. So with the p-value method, we need two things. Number one, we're going to need to compare what is our alpha with the probability of this area that we're looking at. So this is going to be that we want the comparison of the area that it is that we're observing. So in this case, I'm going to say area that z is less than negative 1.64. All right, so this in here is your significance level. And this in here is going to be your p-value. Again, p-value stands for probability value as we then start looking at this. Now, in order to find this p-value, we then need to go back into one of our previous sections to extract, well, what is that p-value that we're looking for? Well, in order to get your p-value, you're going to need your normal CDF. All right, so let's go ahead and let's start extracting this. This is going to be normal CDF. There we are. Now we need area to the left because this is a left tail test. That's going to be negative 1E99. The area, or the area where it stops, or that value where it stops, it's negative 1.64. 1.64. There we are. Or actually, give me 1 second. My apologies. I wrote the wrong one down here. Cheese and crackers. I am so sorry about that. My p-value is actually based off of my test statistic. My apologies. That's negative 2.53. So that's negative 2.53. There we are. So this p-value is going to be based on the test statistic. Okay, so we're basing this off of the test statistic. We found the test statistic, it's negative 2.53, and we're going to base our p-value on that. So once we have the rightmost endpoint here, that negative 2.53, we're going to go through and we're going to identify that we're working with a mean and standard deviation of 0 and 1, respectively. And I'm going to go through to the TI, and I'm going to input this in. So follow me along. Here we are, so we're going to go to that distribution, we're going to go to normal CDF, left was at negative 1 E99, the upper, that's going to be negative, excuse me here, that's going to be negative 2.53, there we are, mean standard deviation is all going to be the same here, 0 and 1, and we get a probability here, or a p-value of 0.0057. So that's what I'm going to be using. Whoops. Here we are. All right. So this value that I got for my p-value was at 0.0057. And the comparison that I need to make here, so again, this was my p-value, the comparison that I need to make here is going to be with my alpha. So making these comparisons, which one is larger? All right, so I'm looking at the larger one. The larger one seems to be this one here in red. That means my alpha level is higher. Now, what does that mean for us? Well, I want you to then look at this piece here. This piece in blue, this 0.0057, is this area in red. That's the area for that test statistic. Now, which area is larger? Is the area in red larger, or is the area in blue larger? Right? Well, naturally the area in blue is going to be larger, which then is going to tell us that my significance level is larger. And we're going to use this nice little aspect. If the P is low, the null must go. So the P is lower, or the P is smaller than my alpha, which then means the P is low, the null must go. That means we're going to reject that null hypothesis. So this is the method of the p-value method, and this method over here, the one that we did first, was that critical region method. You're more than welcome to use either method, whichever one that you would like to use. So now, we need to write a conclusion. So let's go through and let's write this conclusion. All right, what is it that we found? So what we found is that we're rejecting the null hypothesis. So what I'm going to do is I'm going to write a statement, or I'm going to write a sentence that is going to support that rejection of the null hypothesis. All right, because again, that's my decision here. So I'm going to go through and I'm going to say there is, let's say, sufficient evidence to support the claim that the percentage of women ticketed for speeding is less than the percentage of men. And I'm going to say at the significance level of 0.05. All right. So again, I'm writing the statement. The statement says that I am supporting the rejection of the null hypothesis, because again, we're rejecting it because the data Again, the data means here that there is enough evidence to support that claim. So that means we are going with this specific claim here. That means we're rejecting the null hypothesis. So there's a few things that I want to see when I'm writing when I'm grading a hypothesis claim. Number one, did you tell me that you're rejecting or you're failing to reject? All right. So here we're supporting. That means we're rejecting the null hypothesis. So this means that we support the alternative. All right. And what is the alternative? Well, the alternative, that alternative claim is this piece here. So I'm supporting my alternative hypotheses. But again, I don't want to just flat out say I'm supporting my alternative hypothesis. I need to go ahead and verbalize all of this. That way the reader can then go ahead and interpret, oh, okay, great, that's what you initially said. So the math now supports what you were telling me at the beginning. All right, and this only occurs, or this happens, for the level of 0.05. Again, if you use a different level of significance, your outcome might be slightly different, but I doubt that it's going to change your final conclusion. All right, so awesome. We have this down. Now let's go through and let's work on this second example. All right, so take some time, read through it, and we'll go ahead and we'll start extracting everything that we need in just a little bit. All right, so here's what I have so far. For the extraction of the problem that we're looking at. It says that in clinical trials of the anti-inflammatory drug Inflamanex, adult and adolescent allergy patients were randomly divided into two groups. Some patients received 500 millicentigrams of Inflamanex, while some patients received a placebo. Of the 2,103 patients who received Inflamanex, 520 reported bloody noses as a side effect. Of the 1,671 patients who received the placebo, 368 reported bloody noses as a side effect. So the question then becomes, is there significant evidence to conclude that the proportion of Inflamanex users who experience bloody noses as a side effect is greater than the proportion of the placebo group? Okay, so again, what I'm looking at here is I'm looking to extract what is my null and what is my alternative. Now, because my null and alternative, what I'm looking at here, I'm looking at proportion, and this is going to be proportion of Inflamanex users. All right, so proportion of Inflamanex users. I'm going to set that to be my first proportion, and this proportion says greater, so it's going to be greater than the proportion of the placebo group, and that I'm going to label as P2. So this statement now becomes that P1 must be greater than P2. All right, or in other words, proportion 1 is going to be greater than proportion 2. Naturally, our null hypothesis will always be equal to, meaning that there is no difference in the proportions. All right, so once we have this, then we're going to establish, looking at the alternative, what we just set up here, this is going to be a right-tailed test. And because it's going to be a right-tailed test, that's going to cause me to analyze my alpha and not divide by 2, because again, it's only contained in one tail, not two tails. All right, so once we have this, we're going to keep on extracting all the information. We need two different groups. All right, so my first group is the group that I'm going to label for Inflamanex users. All right, so let's see if we can go through this here. Oops, excuse me there. All right, so one side, this is going to be Inflamanex. And the other side is going to be the placebo. Now, for those of you that don't know, the placebo just means that it's a sugar pill. It has no medical qualities behind it. It's just a pill that they give to simulate that somebody is getting real medicine. when they're in fact not getting anything. All right, so here we go, Inflammatory. So for Inflammatory, there were 2,103 patients, and 520 of them reported bloody noses. All right, out of the placebo group, this is going to be our second sample group, there were 1,671 patients, and 368 of them received side effect as a bloody nose. Now I'm going to find my p-hat1 and my p-hat2. p-hat1, that's going to be the 520 divided by 2,103. So again, you can go to your calculator and start making these calculations here. So my first p-value, or my first proportion that I get here, is going to be 0.247. Alright, so I'm going to keep it as 0.247. So this is going to be 0.247. There we are. Now I want to erase all this down here. There we are. Alright, second proportion, this is going to be 368 divided by 1671. So we're going to go through 368 divided by 1671. Oops, excuse me. Divided by, there we go. Alright, in which I get here to be 0.22, and you could say 220, or you could just leave it as 0.22. Alright, so once we have this, we also need this p-bar and this q-bar so that we can work with these test statistics. So let's go ahead and let's find p-bar. P-bar is the addition of the first x1 and x2 divided by their respective sample sizes, which the first one's going to be 2103 and the second one's going to be 1671. Alright, looking pretty good. So this is going to be 520 divided by, or sorry, plus 368. This should get us 888 divided by, and this is going to be 2103 plus 1671. This should be 3774. There we are. Alright, so what I want to do right now is I want to get an approximation to this, just so that I can round this off. And the rounding off for this is going to be 0.235. Now remember, the more decimals you consider, or the more decimals you use, the better off your calculations are going to be. And finally, I want to find q-bar. Alright, so q-bar is going to be 1 minus that amount, so it's just the complement of that amount, which should be somewhere around 0.765. There we are. So let's find that test statistic. So my test statistic in this particular case is going to be P1 minus P2. Alright, and so I'm going to take those considerations here. So I'm going to have here 0.247 minus 0.22. And again, we subtract 0, alright, because we're subtracting P1 minus P2, but they're the exact same amount, and then divided by the pooled amounts. Alright, so we're going to make sure we write those pooled amounts in here. Alright, so here we go. So the first one's going to be 0.235, so 0.235 multiplied by 0.765. Same thing here, 0.235 multiplied by 0.765. And then we're going to divide by the sample sizes respectively, so 2103 and then 1671. And then we take the square root of that. Exactly like that. There we are. So here we have it, where we are able to calculate this test statistic. Now, in order to get the full calculation here, I'm going to go to the TI and I'm going to input this into the TI exactly as I see it. Alright, here we are. So I'm going to go through and I'm going to start with my fraction. Alright, I have a fraction, so I'm going to do the numerator first. The numerator was 0.247 minus 0.22 The denominator, I need a square root. There we are. And then I'm going to use a fraction. There we are. And then the first numerator was at 0.235, and that was going to be multiplied by 0.765. All right, looking good. Now I'm going to go down to the denominator, and that was 2103. Tab on over to the right, get a new fraction going. There we are. Oops. Whoa, whoa, whoa. And tab over. There we go. I forgot the plus sign. My apologies. So here we are, the plus sign, and then we go again, 0.235 multiplied by 0.765. Oops. 0.765, and then divided by, and that's going to be 1671. There we are. And once we're done, you could just go ahead and hit enter. And here we have our z-score. Again, a very reasonable z-score of 1.94. So we're going to go back really quick, and we're going to make sure we write that down. All right, here we are. So we're able to then get a test statistic of 1.94. So again, there's our test statistic. So using this test statistic, what we're going to do really quickly is we're going to create this critical region that we need to observe. Now, because it's a right tail test, I'm going to extract my significance level. My significance level was given to me as 0.01. So 0.01, which means that when I find my critical value, all right, this is going to be z sub alpha, and I'm not dividing by 2 again because it's a right tail test. So I'm going to go through and I'm going to find inverse norm. I need the area, which is 0.01, mean standard deviation, and this is a right tail test. So I'm going to go with the area to the right. So let's go through and let's start extracting this on the TI. All right, here we are. So I'm going to go to the TI distribution. I want inverse norm. Once I have inverse norm, the area is 0.01, and this is area to the right. There we are. And there we are, just exactly as we wrote it down. And we should get about 2.33. All right, again, with rounding techniques, we're going to use 2 decimal places, and that rounds off to 2.33. All right, so here I get 2.33, so there we are. Oops, what was that? There we go, so 2.33. Now, this is our critical value. All right, so we have these 2 items. We have a critical value and we have a test statistic. What we want to do first is we always want to go with the critical value. All right, so let's start going with that critical value. And again, this is a right tail test, which means we only really need the right tail of this Bell distribution. So I'm going to go to 2.33. So I'm going to find it right in here. So this is 2.33, and this is my critical value. And that means area to the right for that critical value. The test statistic here is 1.94. 1.94 falls right in here. So that's 1.94. This is the test statistic. Since the test statistic does not fall in that friend zone, we do not reject, which means we need to fail to reject in this particular case. Fail to reject the null hypotheses. So fail to reject the null hypothesis, this means that when we're looking at the data, there is not enough evidence to support this hypothesis. All right, and again, the way we want to summarize is we want to summarize by saying, hey, by answering the question. And the question was, is there significant evidence to conclude that this hypothesis will hold? And our findings is, no, there's not enough evidence to support that. All right, so let's go through and let's write that down. There is not enough sample evidence to support the claim that the true proportion of Inflammatory users who experienced bloody noses, is greater than the true proportion in the placebo group. And I'm going to say at the 0.01 significance level. And again, what I'm doing here is I'm just summarizing what we found, right? We're not accepting the null hypothesis, right? Because at this point in time, we're not accepting the alternative hypothesis because the way we went through our calculations, there's not enough data. This is not significantly high. It does not exceed that amount, and that amount was at 0.01 significance that we were looking at based off of our data. So at this particular time, we cannot support the claim that we were given. All right, and that's how I want to see those statements, is I want to see the statement that is going to answer the question that is at hand. All right, so again, what you want to do is just write that statement. Now, I'm a little wordy with my statements, and again, at the end of the day, it's fine. I'm not grading on correct grammar or correct punctuation or anything like that. All right, but what I am focused on is for you to make sure that you're getting the correct interpretation by the results that you are getting from your calculator. All right, that is what I'm looking for. Now, for this last part, what we're going to do is we're going to look at the confidence interval for the difference of two population proportions. Now, in here, in this particular case, is what we're going to be looking at when we're looking to create a confidence interval. To create a confidence interval, we need our unbiased estimator. All right, in other words, the point estimate. So, we need this point estimate to occur, and this is what we're looking at, point estimate. These point estimates are your unbiased estimators. All right. So when I ask what is the point estimate, this is what I'm really looking for. What is p hat 1 minus p hat 2? All right. So now that we have this, let's go through and let's go ahead and start extracting everything that we're going to need. Let's look at this example. In this example, we have that a study was conducted to test the effectiveness of a sweetener called xylitol in preventing ear infections in preschool children. In a randomized experiment, 159 preschool children took 5 daily doses of xylitol, and 46 of these children got an ear infection during the 3 months of the study. Meanwhile, 165 children took 5 daily doses of placebo syrup, and 68 of these children got an ear infection during the study. So what we want is to construct a 90% confidence interval. So we want a 90% confidence interval. That's what they're asking us to do here. For the difference, and this is going to be the difference in the proportion of children that got ear infections for the control group and the xylitol group. All right, so here's what I'm looking at. Difference, this means subtract. And I want to subtract the proportion of, let's say, in here, proportion of children that got ear infections for the control group and xylitol group. So the control group here is what I'm going to be denoting as P1, and the xylitol group is going to be P2. All right, so Identifying is the first part. Now we have to go through and find this point estimate. So in order to find the point estimate, we need to go ahead and find what is p hat 1 and p hat 2. In other words, those unbiased estimators. And in order to do that, I'm going to need a few pieces of information that I have within my paragraph. Alright, so here we go. Now, I said P1, this is going to be sample 1, and this is the people who were in the control group, so this is your placebo. Sample 2 is going to be everybody who took xylitol. Alright, so all we need to do is just extract. So N1, how many children were in this placebo group? Alright, let's see if we can find how many preschool children took the placebo. 165 children took the placebo, so that's going to be 165 that took the placebo. And let's see how many of them reported that they had a bloody nose. So 68 of them. There we are. And sub 2, meaning our sample size, the preschool children who took xylitol, this was 159 of them. And how many of them reported bloody noses? Which was 46 of them. And now that we have this, we can generate p hat 1 and we can generate p hat 2. P hat 1 is going to be 68 divided by 165. P hat 2 is going to be 46 divided by 159. Alright, so let's extract these here. So I'm going to take these numbers into my calculator, divided by 165, and I should get an approximation for 0.412. There we are, not too bad. And then 46 divided by 159. And that's going to be approximately 0.289 as such. There we are. All right, looking pretty good so far. Now, in order for us to be able to find the error, we're also going to need to know what are the Q values for this. So we need to know what is Q hat 1 and what is Q hat 2. Alright, if p hat 1 is 0.412, then the complement of that must be 0.5. Oops, excuse me. The complement should be here 0.588. And then the complement for p hat 2 should be 0.711. There we are. Alright, so let's start answering the question. What's a point estimate? Well, the point estimate is going to be the difference there. Alright, so P1 minus P2 hat. There we are. Alright, so P1, here we are, 0.412 minus 0.289. The difference in the proportion of the children that got ear infections. All right. So I'm just making sure I double check the values that were given to me are in the correct place. All right, here we go. So this value, again, if we input this into our calculator, we should get a really nice value of somewhere along the lines of 0.123. All right, again, not too bad. So take some time, again, and run these calculations for yourself and make sure that you're getting the right values. So now we need to determine what is the critical value. Now, because this is a confidence interval, an interval means that we need two parts to this. One at the top end, we need a bound at the top and we need a bound at the bottom. Because of that, it turns it into this two-tail value. So we need to then find what is z sub alpha over 2, because again, we're working with this two-tailed test. So what I'm going to do really quickly is I'm going to extract here what was my significance level, or what was my confidence level. Well, my confidence level was 90%. In other words, this was 0.9, which means my alpha level is 1 minus that 90%, or 1 minus 0.9, which means alpha must be 0.1. Now alpha over 2, because we need to cut it in half, alpha over 2 is going to be half of this, which is 0.05. All right, not too bad. So what we have here is that two-tailed test. So let's keep going. All right, now what I'm going to do here is I'm going to find this inverse norm. All right, I need the area. Now I'm actually going to use the area on my calculator. The area on my calculator, because this is a two-tail, 0.901, and then I'm going to use center. If you don't have a TI-84, you're not going to be able to use center, and then you'd go through this whole calculation to be 0.05, and you would just use left or right tail test. All right, but then at this point in time, since we have a TI-84, we can use that center argument. So let's go through the calculator and find it. Here we are. So I'm going to go to inverse norm. There we are. The area that I want is that 90% area. There we are, 0, 1, and that area is in the center. And I'm going to paste that. There we go. And here's my z-scores, negative 1.64 and 1.64. So those are the two values that I need, but I'm only, again, considering one. So here we go. The value that I need is going to be that 1.64. Awesome. So now we're going to have to find this margin of error. So to find the margin of error, we need the formula that we were initially looking at right up here at the very beginning. Whoa. Here we go. There we are. So we need this formula that we were working with right at the very beginning that was listed here. To find the error, we need the z-score, and then we're going to need that standard deviation for these two proportions. So let's go through and let's start writing this out. All right, I'm going to need z sub alpha over 2, and this is going to be multiplied by p hat 1, q hat 1, divided by n1, plus p hat 2, q hat 2 divided by n2, and we're going to take the square root of this. All right, so making our insertions here, we have a z-score of 1.64, and we're going to multiply this by the square root, and then we need p hat and q hat. The good part about this is that we've done the calculations for this. There we are. We've done the calculations for this. P hat is 0.412, and then q hat 1 is 0.588. N sub 1, that's going to be our first sample, 165. The next one's going to be 0.289 multiplied by q hat 2, which is 0.711, divided by 159. There we are. And what I'm going to do again is go to the TI-84, and I'm going to insert this calculation exactly as it is. All right, so keep this in mind, and we're going to go put this onto the TI-84. All right, so here's my calculator. So I cleared it, just making everything a little bit more convoluted. So I'm going to put in 1.64 multiplied by the square root, and I need my fraction here. Fraction for, let's see, that was 0.289, 0.289, and that was going to be multiplied by 0.711 divided by 159, tab on over, plus another fraction, same numerator, 0.289 multiplied by 0.711 divided by the second sample size, which was 165. And there we are. All we need to do is hit enter. And we get this error to be about 0.826. All right. So, oh, excuse me. Yep, I made a fudge. Oh my goodness. Okay. I'm going to select this, press enter, and in doing so it lets me do some recalculations here. So the second one is not 0.289, it's 0.412 multiplied by 0.588. 588. There we are. And there we go. That's a little bit better. So 0.86 is the error that we're looking at. So let's go back and let's modify things. All right, here we are. So my error, the error that we just got, was at 0.86. Cheese and crackers, 0.086. There we are. So if we want to construct the confidence interval then just becomes the point estimate, which was at 0.123, and then we subtract the error, which is 0.086 less than P1 minus P2, and then the point estimate, 0.123, plus the error, once again, 0.86. There we are. So what we have here at this point in time is we have this confidence interval, which in this particular case, if we go through the calculations, let's see, 0.123 minus 0.086, this should get us 0.037 is less than P1 minus P2, which is going to be greater than 0. And this should be about 209. All right, just change that minus into a plus, and yep, 0.209. Great. So this is my confidence interval. Now, let's see, does it appear that the sweetener is effective at reducing ear infections? So this is now the question that we have to answer. So did we construct the interval? Yes, we did. The interval's right here. Now, does it appear that the sweetener is effective in reducing ear infections? So that is something that we must now try to observe and dissect. So we're only going to base this off of the data that we're looking at. So here goes the interpretation. All right, this estimate was built because of these samples. So let's look at the samples here. Sample 1 was greater than sample 2. All right, so sample 1 was everybody who took the placebo effect. Sample 2 was everybody that was taking xylitol. When we calculate this difference is positive. So what I'm looking at here, I'm going to write this in green. Difference in proportion remains positive. Now, what I mean by remains positive, all right, look at this difference here, which was 0.123. It remained positive, all right. Not only did that occur, let's look at these values here. The left endmost value for this confidence interval is a positive number. The rightmost value is another positive number. What does that mean then? Well, that means that this confidence interval, 90% of the samples that we take, this will always occur where the difference in the population proportions will always fall within this interval 90% of the time. All right, so that means the difference in the population proportion will always be positive, meaning that there is a significant difference. All right, now, because there is a significant difference, well, is it going to prevent ear infections or not? Well, this means when I'm looking at sample 1 and sample 2, sample 1, I was looking at this value. Sample 2, I was looking at this value. Sample 2 placed higher, or sorry, sample 1 placed higher in relation to their proportion. Sample 2 placed lower. So who had the lowest amount of ear infections? And that's the xylitol group. So is this effective? Yes. Yes. It appears that xylitol is effective in reducing ear infections. And this is going to be since the difference in proportions creates a positive interval. Now, that's then going to tell me that my proportion, the true population proportion, P1, will always be greater. This means that there will always be more children that have ear infections that are on the placebo, which means these values, since P2 is not large enough for these values to be negative, then P1 will always be larger, meaning that children that are taking xylitol will always have less bloody noses than those who do not. That's what we're summarizing here. All right, so how is this going to look on an exam? Well, on an exam, I will give you a question like this, and the question is going to be broken down with each individual piece here. It's going to say, hey, can you find the point estimate first? Next, can you determine the critical value? Next, can you find the margin of error? So exactly as you see this question and its breakdown is exactly how you're going to see it on your next exam. All right, same thing's going to happen here when we talk about running a hypothesis test. Again, I'm going to give you the prompt and then I'm going to give you the sub parts to it. Can you identify the null and the alternative? Can you find the test statistic? Use either the p-value or the critical value. There are some questions where I want you to use specifically the p-value method and others where I'm going to want that critical value region as your method. And then there's also some questions that say, hey, use whatever method you feel more comfortable with. All right, I'm going to be looking for a decision about the null hypothesis and then a conclusion. Remember, your conclusion can be 3 different outcomes. It can be a type 1 error, it can be a type 2 error, or it can be a correct decision. So those are the only 3 possible outcomes that we can see for a conclusion. Depending on your conclusion, it might be that you got everything correct and you arrived at the correct decision, or it could be that you made a type 1 or a type 2 error when I'm reading and grading these problems. All right, so I hope you all enjoyed this lesson for section 9.1, and I will see you all next for section 9.2.